Welcome back. We are here in chapter 18 now, where we are going to be talking about aqueous ionic equilibrium. If you are listening to this during the spring break, good for you. You're trying to get ahead. If you're listening to it after the spring break, good for you. You took a good break. All two strategies are really good. So, what are we going to do on this chapter? We're going to define terms associated with acid and bases. So you have a little bit of this on 1411. So we're going to go deeper into these concepts. Specifically, we're going to be talking about common ion effect related to the equilibrium systems and buffer systems, which is something specific that happens when you're dealing with acid and bases on equilibrium systems. After that, we're going to see or review how we measure pH, what pH is, and how we calculate it for buffer system using the Henderson-Hasselbalch equation. And then we're going to go into one of your favorite subjects, which are going to be titrations. And for titrations, we're going to have to track them through the process and see how that affects the equilibrium systems that we have been dealing with. And after we're done with acid and bases, we're going to move into solubility products, which is what you did on 1411 with the solubility tables, but in reality. So what does it really happens equilibrium-wise? How come some ionic compounds are not soluble in water and others are? And for the most part, every ionic compound is going to be somewhat soluble in water, even if it's to the 10 to the minus 64. But there's some solubility in there just because of pure mechanical forces. So when we do that, we're going to talk about how we define solubility in terms of equilibrium, how we write a new equilibrium constant, which is going to be Kp for the solubility, Ksp for the equilibrium for the solubility product. And we're going to see how we're going to express that, which is nothing more than doing a heterogeneous equilibrium expression. And then we're going to see how we can predict any formation of a precipitate, but not like we did it on 1411 with a table, but with the calculations we're going to do based on the equilibrium constants. So that's what we're going for in this chapter. It's one of my favorite chapters, especially the titration, because it requires a lot of critical thinking. So let's begin with these two concepts, common ion effect and buffer system. Let's define first what common ion effect is. Well, let's say that you have an equilibrium system. And we can basically say that the equilibrium is happening on a container where you're going to have A and B present, making C. And because this is an equilibrium system, all species will be present at all times. And the formation or destruction of the product happens at the same rate because it has reached an equilibrium status. So what will happen to that equilibrium if I increase C? So this is nothing more than the Le Chatelier principle that you already know. That would cause the system to turn toward the reactants, bringing down C back to equilibrium again. So the question is, how did we get this up? Well, because we added to it. So we can say that we took some XC solid, which is not A, B, or C, is something new, and we put it there. And that was soluble, and it broke into something like that. So now you just basically increase. You don't pay too much attention to the negative charge because I just made it up. So pay attention to the fact that I added C. So I just effectively increase the concentration of C by adding a new salt. So that's what we call a common ion effect. So a common ion will make C, in this case, go up, which will affect the equilibrium system via the Le Chatelier principle. So that's what a common ion effect is. Adding something to the solution that is already there, that is common to it. So let's do a problem based on that to see how that works. In which of these solutions does nitrous acid ionizes less than it does in pure water? So before we proceed and start doing numbers, let's make sure we understand this problem. In which of these solutions, okay, so these are going to be all solutions, right? Which is basically telling me that they are, if it doesn't tell me anything different, I'm going to assume they're aqueous solutions because this planet is over 70% water. And it's telling me that the nitrous acid is going to ionize. So it's going to produce ions, right? And it's happening in pure water. So the first thing we have to do with a problem like this is write a chemical equation. So the nitrous acid is being ionized in pure water. Nitrous acid is a weak acid, so you should know that, right? So it's going to create an equilibrium because it's a weak acid, and it's being ionized. So what do acids do? Acids donate or produce hydronium or protons, right? So the acid is going to turn into its conjugate base. So all terms that you already know. And the water is going to turn, which is acting as a base because it's in the presence of an acid stronger than itself. It's going to behave like a base and it's going to accept that proton. Therefore, the solution became ionized. So that's the equation that you have to consider first. And make sure it's balanced, and it's balanced, right? So the question is, when I add any of these solutions, would that cause us to ionize less than it does in pure water? What does ionize less means? Ionize less means that it's going to tend toward the reactants. So away from the ions, ionize less. So as long as we understand that, we are on a good track. So what will cause that? The only thing that will cause that is increasing any of the products or decreasing any of the reactants. So you're going to have option A, increasing any of the products, or option B, decreasing any of the reactants. So let's look at sodium chloride. Sodium chloride, when I put it in pure water, is going to give me Na plus aqueous and Cl negative. And here once more, you have to go back to something you learned. You put a salt in water, does that salt affect somehow the water? Does it make it more acidic or more basic? So when I put this in water, the possibilities, based on what you already know, are that it's going to give me NaOH plus H plus. So that's what that's going to create. Will that increase the products or decrease the reactants? Because that's the only thing that is going to cause the equilibrium to turn toward the reactants, therefore causing less ionization. So let's see. If I am adding protons, I am increasing this. Can everybody see that? If I am adding protons to the water, that would increase that. However, hold your horses. if sodium goes into water, it's going to create sodium hydroxide. Sodium hydroxide is a strong base. So this will not happen because it will tend to go that way. So this is not going to happen. So you're not going to create any protons. So this is not going to go up because the sodium is not going to cause anything to water. So hopefully when we study that back on chapter 17, you pay attention because this is going to be extremely important. So the sodium is not going to do anything to it. So it's just an ion floating around. What about the chloride? When you put the chloride in water, it's going to give you HCl and hydroxide. The formation of hydroxide will react with the proton producing water and it will bring this down. So if that were to happen, that would not produce less ionization because it will make it go toward the products to bring back the hydronium. However, hold your horses. Let's see if this is even happening before we go there. So you are creating hydrochloric acid. What do we know about hydrochloric acid? Hydrochloric acid is a strong acid, so this will not happen because it's going to go that way. So once more, since this is not happening, you're not creating any hydroxide, which means you are not consuming any hydronium, which means since this didn't even happen, that doesn't affect the equilibrium. So you can say then with very confidently that these ones have no effect. What about the potassium nitrate? Potassium nitrate, when you put this in water, this creates nitric acid, which is a strong acid. This creates potassium hydroxide. And as you notice, I am not doing the equation anymore because you learned that on chapter 17. So if you need to see where the KOH is coming from, go back and review the effects on salts on solutions. And this is also a strong base. So that's not going to be created because that's a strong base. That is not going to be created because that's a strong acid. So these will have no effect either. What about the next one? The next one is sodium hydroxide. We already know that the sodium will create in water more sodium hydroxide, and the OH is going to create water. So water doesn't affect anything. It's just going to make it more diluted. So you shouldn't have any effect on that one either. What about sodium nitrite? That's going to give me Na plus and NO2 negative. We know this is going to create NaOH in water, which is a strong base, so that's not going to happen. However, what about the nitrite? The nitrite, if I put it in water, is going to give me nitrous acid and hydroxide. This will definitely affect my system. And this is going to be a weak acid, so that's going to create an equilibrium. So this will be present, this will be present, and this will be present at all times. So the creation of the hydroxide is gonna consume some of the hydronium that I'm creating, which is gonna bring this one down, not up like I need it to be. So this will not ionize less. This will not cause the nitrite to ionize less. it will be more. So that will be this creation of the hydroxide is not gonna cost that. However, I did create more uh, nitrous acid. So that's gonna bring this up, which it actually is gonna not less, but it's gonna cause more ionization. So that will not either cause the less ionization of the nitrous acid. So the answer is none of them will cause less ionization. All of them will cause nothing or higher ionization. So this problem requires that you check everything. So let's review what we did on this problem, or what we needed to know on this problem. You needed to know how to write the ionization equation for an acid. You needed to be able to recognize between weak and strong acids. You needed to be able to understand how the solubility of salts affects the acidity of a solution by knowing if you're forming or not forming an equilibrium or a strong or a base or acid. And you needed to understand the Le Chatelier's principle. So if you're having problem with this particular problem, I strongly recommend that you go back and review in full the whole chapter 17. That means you didn't master those concepts. So you need to master chapter 17 to be able to do well on this chapter. And this is the easy part of this chapter. Not trying to scare you, just telling you you need to master chapter 17 before you proceed. So with that in mind, you should be able to do daily wear 18.1. Few things that I want you to keep in mind when you do this. Make sure we understand what this is asking. A formic acid solution. So make sure you find the formula for formic acid solution, and you can do the reaction in water. And it's going to have a pH of 3.25. Which of these substances raises the pH of the solution upon addition? So raising the pH means that it's going to become more basic, which means the hydronium concentration is going down. You already know how to go from pH to hydronium concentration, right? Hydronium concentration equals 10 to the minus pH, right? You learned that on chapter 17. So you're trying to see what situation or which one of these substances will cause the hydronium concentration to go down, which will make it more as basic, which will mean it is raising the pH. So you're gonna do what I did on the other ones with each one of these to see if it's gonna decrease the hydrogen concentration, which is raising the pH because it's more basic. So keep that in mind when you're working this problem. And once you are done with that, let's continue here. So let's do this problem. What is the pH? So we're looking for pH, right? So we know since we're looking for pH, we're going to have to be able to do something like this, the minus log of the hydronium concentration. So we're looking for the hydronium concentration. That's what we need to find out. So what is the pH of a solution made by adding 0.30 moles of acetic acid and 0.30 moles of sodium acetate? So acetic acid is right here. So this is the formula for acetic acid on the table. And this is the formula for the acetate. So the first thing we have to do, and it's giving us the moles, 0.30 of acetic acid and 0.30 of sodium acetate, and it's telling us that it's in 1 liter of solution. So 0.30 divided by 1, that's my molarity. So the molarity is the same number, but moles over liters, because we divided by 1, right? So the way to do this problem is by doing an ice table. Because the ice table is going to allow you to find the hydronium. And the question is how? Well, the question is how is because you're going to do the balance equation. So acetic acid is going to ionize into a proton and acetate. And because you know that, then you can do the equilibrium expression. So the equilibrium expression is going to be products over the reactants to the proper powers based on the coefficients. And all of this is 1 for all of the coefficients. And if you go into the book, it tells you that the Ka is 1.8 10 to the minus 5. So since we need to find the pH, all we need to do is to find the proton or hydronium concentration. The water is not included here, so that's why you see protons and not hydronium. But if you find the protons, you find it the hydronium, right? So how are we going to do that? Well, we're going to use the ice table. We're going to know the initial of the acetic acid. And we're going to know the initial of the acetate because it was given to us, right? So it was given right there. Sodium acetate and acetic acid. And how much hydronium we have, or protons, we don't know. Well, we know. We know at the beginning we have 0 because nothing has happened yet. So the reaction is all 1 to 1. So doing what you already know to do with the ice tables, you know that the reactant is going to go down by X and the product is going to go up by X. And you have 2 products, so you're going to have 2 X's there, right? So the best you can do is to express it using equilibrium concentrations. So you're going to have that expression, and that expression. So that's what you're going to have on your ice table, for which we only care about the equilibrium concentrations. Because as you already know, now we can take the acetic acid and we can put it there, and we can take that, put it there, and we can take that and put it there. When we do that, we're going to have something like that. And we know the value of the Ka, right? However, given that this Ka is so small, whenever you are around 10 to the minus 5, 10 to the minus 6, feel free to use the X approximation. We're saying that X is based on 10 to the minus 5 compared to 0.30, is way too small to cause any changes when we use significant figures. So which means we can rewrite the equilibrium concentration that way. So the X that we are adding or subtracting can be gone. Not the X by itself, but the X that is being added or subtracted is going to be insignificant. So instead of having 0.30 to the X, we can just put 0.30 on both sides. And that makes this a very easy operation. So just by using the algebra we know, we can say now that X equals 1.8 to the minus 5. Let me see, I'm missing something here. Where's my... Just a second, trying to find out where it's hiding there. And we know that this will cancel with that because they're the same. So that's what we're getting. X equals the Ka, and X is the same as the hydronium or proton concentration in this case. So when we do that, then we can apply the formula for the pH, and our answer comes out to be 4.74. So let's go back to the original problem. So our answer was 4.74. The original problem was to find the pH when we add those two together. And we come out with a 4.74, which is a acidic pH. And based on the fact that we're adding basically equal amounts of acetic acid and sodium acetate, that will make sense based on the equilibrium constant. So always make sure that your answer makes sense. So with that in mind, knowing that a problem like this, you approach it by using the ice table and everything you know. The first thing you have to do is to do a balanced equation. And if you notice, you are adding what you have is you have the acid and the conjugate base present from the beginning, which is going to be what we're going to see is the definition of a buffer system. When the acid and the conjugate pair, or the base and the conjugate acid pair, are both present from the beginning on the solution, and you're controlling how much you're putting in there. So more to come on that. So with that said, you should be able to do this problem. The answer is going to be x equals 1.2⁻⁴, which is going to give you a pH of 3.86. And this one, the Ka is 1.8 10⁻⁴. I would still feel confident that you can use the X approximation for this one also. And after you do that, do this one also so you can practice some more. The only difference on this one, you're using now a Kb. So you need to know what's happening here. Is the substance behaving like a base, or is the substance behaving like an acid? Begin by writing a balanced equation of the ionization or the reaction with water. And that should be more than enough for now. So make sure that review chapter 17 is unit 2. Make sure that you truly understand all these concepts that we cover in part A, because you're going to need those to be able to proceed. So until the next time, let me know if you have any questions or concerns. See you later.